Let's see now how to query. For a query, the question is always how to find the minimum from left to right, from the left boundary to the right boundary. In the segment tree, there are three rules. If the current node's interval, let's call it xy, is completely outside the boundaries left and right, which means there are no overlap. In this case, we return infinity because we are looking for the minimum. That's why we return the infinity plus infinity, the maximum value. We have to return the maximum value. If the current node's interval xy is totally in the interval left and right bound, which means we have a total overlap. In this case, we return the value at that node. Third case, if the interval is partially overlapped. We have a partial overlap here. The interval xy, not completely inside the left and the right node. We have a partial. In this case, we look both on the left and the right side of that node. We look for the minimum, we look for the left, and then for the right side. Let's understand the overlaps cases, the overlap cases. Let's call start and the interval of the current node in the segment tree, and of course L and R, the interval of the SRMQ, the range minimum query. As you see in the left picture here, the left image, the interval of the node is completely inside the left and the right boundary, which means we have a total overlap. In this case, we have to look if the left boundary L is less or equal than the start, and the right and also the right boundary must be greater than the end of the interval of the node. If we have no overlap, we have two cases. If L, the left boundary, is greater than the end of the interval of that node, or the right boundary is less than the start. We have two cases here, which means this interval is completely outside. We have this first case, or this case too. Okay, let's see an example. If we have our original array here, original array A, that contains these values, and we are looking for the minimum between the index 2 and 4, which means 2 to 4 here. Using the segment tree, first, of course, we have to build the segment tree as we have seen in the previous part. Then we have to test or to check if 2, 4 and 0, 5, which means the current node interval and the left and the right one. Here, as you see, we have a total overlap. 2, 4. We have partial overlap. 2, 4, partial overlap 0, 5. See here, 2, 4 in the purple color. Partial overlap 0, 5, which means 2, 4 is a part. 0, 5, 0 is a part of 2, 4. As you see, 0, 5 is a part of 2, 4, not completely inside 2, 4. So in this case, we have to look on the left side and the right side of that node. check the left. Start by the left always here. We have to check 2402. The interval of this node is 02, and we have also 24 the left and the right node. 24 here is also partially overlap 02. We have 2 in common. So we have a partial overlap. We go left and we go right. And we check for 2401. As you see here, there is no overlap. That doesn't 24 doesn't overlap 01. So from the node 3 here we return, because we're looking for the minimum. There is nothing we find nothing here. We return plus infinity. And we go to the right side from the node -1 here. We check it. 24 and 22. 24 totally overlap 22, which means 22 is completely inside 24, because 2 is completely in the interval 24. So here we return the value of that node, which is -1. Now we can calculate the minimum or the value or the return result of that node -1, which is the minimum between plus infinity and -1, which is -1. And we go to the right side from the node -10, and we check 3.5 partially overlap 2.4, which means the 3.5 is a part of 2.4. 3.5 is a part of 2.4, as you see in the picture. So we go left. We go left and right. We check the left side. 2.4 and 3.4. You see here, 3.4 is completely inside 2.4. So we have a total overlap. So we turn here the value of that node, 2. We check the right side of this node. It's node -10 here. 2.4 and 5.5. But you see, 5 is completely outside 2.4, which means there are no overlap. So we return plus infinity. We can compute now the value of that node, which is the minimum of plus infinity and 2, which is 2. Now we have the value at the root here. We can compute it. The value, return value from the left side is -1, and the return value of the right side is 2. We can compute the minimum between them, which is -1. So we can say that in the original array, that the minimum from 2 to 4 is -1. Let's see the function, the recursive function using an array here. We took as parameters the segment tree, the built segment tree that we have built in the previous part, the start position of the root, which is 0, of course, and the end position. I'm talking about the first call here. The first call will be like this. We give the segment tree the interval of the root from 0 to -1 and the position of the root, which is at position 0 in the array. This is the first call of this function. So in general, we have the start position of the node, the end position of the node, and sorry, here I forget left boundary and the right boundary, and of course the position of the node. You have to give the left and the right boundary. And we check if there are no overlap, which means, as we have seen in the pictures in the previous slide, if the left boundary is greater than the end position of that node, and the right boundary is less, or the left right boundary is less than start position. We return plus infinity. If there is a total overlap, we return that value. Otherwise, we compute the middle, and we go left and we go check the minimum between the left and the right. We return the minimum between the sub left tree and the left sub tree and the right sub tree. Okay. Let's see the time complexity of this. In the worst case, I will check all the nodes here. This is in the worst case. So in general, we have to run in the depth of the tree or the height of the tree. We have to run onto the height of the tree. So the time complexity, it will be in the worst case big O of the height of the tree. And like we have seen in the previous part, we can compute this height using the number of nodes in the segment tree. Using this formula, we know this in one node formula. So we can say that at the first level we have one node, then two nodes, then four nodes, and so on until the height. At the last level here, we have 2 power I h minus 1 nodes, which h is the height of the segment tree. So we can say that m plus 1 is equal to 2 power h. We can use the formula of the natural logarithm of m plus 1 is equal to h times the natural logarithm of 2. So we can say that h is equal to log base 2 of m plus 1. So we can say that the time complexity is of this function it will be a big O log base 2 of m, where m is the number of nodes in the segment tree, and we can compute it, of course, in a function of n, which will equal 2 times n minus 1. N it will be equal to m, or m, as we have seen in the previous part, it will be equal log base 2 of m. Let's try to code this using first an array. In the previous part, we have seen how to build the segment tree using an array. We have to compute, as we have said, to compute the size. It will be a power of 2. Okay. And we can build the segment tree using this recursive function. Now, let's try to let's call it range query. Or SRMQ. It's better. It will take the segment tree that we have built and the start position and the last position of the node. Okay. Of course, the left boundary and the right boundary of the query, and the position of the current node. We check first if there are no overlaps, which means, as we have said, that if L is, I forget, I think here, if L is greater than the end, and okay, if L is greater than the end position, and the right boundary is less than the start position. In this case, we return unvaried. I think we have unvaried here. Okay. Then now check if we have a total overlap. Here we have all. And right is greater than the end position of the current node. So we return the value at that position. Otherwise, we compute the middle, which is the start position plus the end position over 2, and we return the minimum of the left subtree and the right subtree. So we call the function recursively here. It will be start position. This is the left subtree. The left and the right remain the same. Of course, and the position will be +1 for the left subtree. Same with the right subtree. I think here +2. Middle +1. This is the left subtree, 2, and the position. Let's try it here. Let's compute this. Let's call that function Q. We use the segment tree. Of course, the position of the root, the interval of the root, n-1. Call it n. Yes. The left boundary, the right boundary, and the position of the root and the segment tree. I hope there is no error here. Of course, we have to call the namespace here as standard namespace. Okay. Okay. The famous error. Okay. Failed here. 2114. Well, of course, yes, because of this. We need now to display the segment tree, and think because of this. Okay. That's right. I don't know. Let's start here. Let's put a test case here. Let's say we have 3 test cases. Let's say from 1 to 6. And from 1, 2, 3, 4. Let's say from 3 to 4. And let's say now for 1 to 2. The answer, it will be from 1 to 6, it will be -10 for the first one, for the first test case. From 3 to 4, 1, 2, 3, 4, it will be -1. Must be -1. And from 1 to 2, it will be 3. Let's try it. Okay, it's correct. Let's try to submit it in our our problem here, our line judge. Login. Okay, let's change the theme. Range queries. What are they? Range queries. Queries. Static minimum. Let's wait to submit the code. Okay, here, where is it? I have called the file. I forgot the name of the file here. Sorry for this, guys. Our SRMQ segment 3. Okay. That's segment 3. I think. No. Sorry. Okay, this one. If you segment 3 array. Okay. As you see, using the segment tree, we have resolved that problem. Static range minimum queries. Let's talk about the time complexity of this whole code. We have seen that the time complexity of this function is O log base 2 of m, where m is the number of the node in the whole segment tree. I think we have a mistake here. This is not the definition of the build function. It's the definition of the segment tree here. Sorry about this, guys. Here, okay, time complexity is O log base 2 of m, where m is the size of the segment tree. The whole type complexity is O big O of m of the build function, and q times log base 2 or log m of the queries. Let's code it using pointers. As we have seen in the previous part, we have defined this node structure that contains the value on the left side of the left node, the right node, and the two constructors here to build the node. And we have used this structure to build the segment tree, as we have seen on the previous part. Now, let's check it quickly. The result of this, we have developed a level order function to display the segment tree by levels. Here, of course, you see minus 10, minus 1, minus 10. This is correct. Okay. I think we don't need this now. Let's delete this call. And let's define the SRMQ. Let's implement the SRMQ function. It will take as parameters the segment tree, the pointer to the root of the segment tree. Then the start position, let's call it S for now, and position of that node. We don't need the position. We need only the left boundary and the right boundary of the RMQ, and we don't need the position of that node because we don't use an array. We use pointers. Same as the previous implementation. We have to check the case of no overlap, the case of, let's take a copy paste here to gain some time. Okay, we have to check if we have a overlap case, no overlap case, or total overlap, or partial overlap. Okay, I think, okay, and okay, okay. Here it's okay. Well, in case when there are no overlaps, we return the infinity. In the case we have a total overlap, we return the value at that node, which is root here. If there are a partial overlap, we compute the minimum. We go to the left side. And so no need for this because we don't have an array here. And we go to the left side, right side, and the left side and the right side. Okay. Let's call it here. It's very simple, as you see. If you understand how to build this array using this structure, how to build this segment tree using this structure, you can easily understand how to recursively call a function to compute that RMQ. RMQ, I call it here seg, I think. As usual, the first node is at the interval of the root in the form 0 to n-1, and here we have the left boundary and the right boundary. I think okay. Left, yeah. Let's try it. Side on. Okay. Let's submit and line judge. I think SRMQ segment tree here. Okay, this one. Okay, is accepted. The time complexity is the same as the previous code using the array. You can practice on the same online judge. Try to use the segment tree, how to compute the static range sum queries resolving this task, and the range XR queries. I think this task is static too, it's not dynamic. try to practice, guys, on these two problems to understand or to put all together to understand how to use a segmented tree to resolve these two tasks.